see if that works. Could I maybe put one of each on each side? So we'll go through and see if that idea works out. So that's putting one of each on each side as opposed to both on the same side over here. Right now, they both have 5 bonds, that's 10 electrons. Gonna need 14 more electrons. Can I put 6 more electrons around each chlorine? That'll take care of 12 of the 14. Do that over here. And so far, that'll be 22 electrons. Now I need to put one more pair on one carbon or the other, doesn't really matter which. Do I need to put in a double bond there now? This one's only got 6 electrons, this one has 8, so this one's short of the octet one. Now I am going to need to do a double bond. These are called isomers of each other. Isomers mean same formula with different shape. They have a sort of different shape. One has 2 chlorines on one side, the other only has 1 on each side. So partly I did this so I could throw out the name isomer, so I just realized I'd forgotten to talk about those. And there's a third isomer as well, but we'll not worry about the third isomer right now. We'll move on to the next topic. If I have a molecule like hydrogen, both hydrogen atoms have an equal pull on the 2 electrons that make up the bond, an equal attraction to those 2 electrons. Are the electrons equally shared here? Yeah. In this case, we're talking about covalent bond, and we define that as sharing the electrons. These 2 are identical atoms, therefore the electrons are exactly equally shared. That makes it a nonpolar bond. If I was talking about an ionic bond, we don't have the electrons shared. There's been electron transfer. Got a -1 on the chlorine, +1 on the sodium. Is it possible to have something in between, completely equally shared, totally unequally shared? Some sharing, but not exactly equal sharing? That might be something like hydrogen chloride. What's the approximate effective nuclear charge on hydrogen? Is it sort of related to group number? So the electrons near hydrogen are feeling about a +1 charge coming from the nucleus. Is the effective nuclear charge for chlorine going to be greater than that? It's group number 7A, so its effective nuclear charge is a function of 7. The chlorine has a much greater effective nuclear charge. I've got a pair of electrons here. Will they be equally shared between the hydrogen, which is pulling with sort of a +1 charge, and the chloride, which is pulling with closer to a 6 or 7 charge? Would the chlorine pull the electrons more towards it and away from the hydrogen somewhat? But it's still going to be a covalent bond. If I have 2 nonmetals, both of these are nonmetal, hydrogen are both nonmetal, so we're going to have a covalent bond. Some of you have already probably run into the idea of electronegativity. Electronegativity is the pull an atom has on the electrons in a bond. So if I have a bond HCl. The hydrogen's gonna have a pull on that electron cloud, the chlorine's also gonna have a pull, but they may not be equal pulls. And that's gonna be decided by the size of the numerical value for electronegativity. Does it already seem like maybe chlorine will pull electrons towards itself? We're gonna have various symbols that indicate that electrons are being pulled in one direction or another in a bond. That arrow is one way to show it, it's not the most common way, but it's one way we'll use as a symbol later on this semester. So what it's saying is it's pulling electrons away from the hydrogen towards the chlorine. A little bit of a weird arrow, because this is their sort of a positive at the end here. If I pull electrons away from an atom, will that leave a bit of a positive charge there? And add electrons to the other atom, making that other atom somewhat negative? Will this chloride be a full negative one, like it is over here? No, it's partly between neutral, zero charge, and partly between a full negative one, so it's a partial charge. Maybe it's 0.1 negative, maybe it's 0.25 negative. The more common symbol that we'll use is, we'll say that chlorine is partial negative. So technically that's a lowercase delta, sort of a D with a curl on the top of it. And since the chlorine gets extra electron density, put a negative there. If this is, say, a negative 0.1, then the hydrogen in turn also has to be a positive 0.1. Altogether, the whole molecule still, it has to be neutral, has to add up to zero. So if one side's a little bit negative charged, the other side has to be correspondingly positively charged. Does that make some sense? Does it seem like we're talking about a bunch of numbers that you're gonna have to memorize now? So electronegativity, that's a measurement of how much pull an atom has on electrons in a bond. So if you bond two atoms together, they're gonna be pulling electrons towards themselves. Since these are both hydrogen, hydrogen does have a value for electronegativity. I'll talk about that in a moment. But wouldn't it be exactly equal? Aren't both hydrogens going to have the same electronegativity? If the electronegativity is exactly the same, the electrons are going to be equally shared, and I'll have a nonpolar bond. Over here, unequally shared. I get a polar covalent bond. If I have electron transfer, that makes it an ionic bond. Sometimes if you just take an introductory chemistry class, they don't talk much about these polar covalent bonds, but in reality, most bonds are going to be at least slightly polar. So most covalent bonds are going to be polar covalent bonds unless they're identical atoms. So electronegativity is a combination of factors we've already talked about: size of the atom, effective nuclear charge, ionization energy, all of those factors that we talked about. Those factors were all about individual atoms. Now we're talking about atoms that are bonded to other atoms, so that's why we have this different term, electronegativity, because we're talking about bonds now, not individual molecules. When I combine all of the effects together, turns out that the greatest pull on electrons is in the upper right-hand corner. That's the direction of increasing electronegativity. How strong is the electronegativity for helium? Oops, sorry, I dropped the pen. Trick question. How strong is the electronegativity on helium?
Doesn't helium have a full valence shell?
Yeah, but So we've got two answers here, both are basically correct. Does it have an electronegativity? It doesn't like to form bonds because it has a full valence shell already. So helium, neon, noble gases in general, you won't find an electronegativity value for them because they don't like to form bonds. Electronegativity can only be measured in bonds. Since helium and neon can't form bonds, you can't measure the electronegativity of helium and neon. That means the most electronegative element is which one? Fluorine. I throw fluorine up here. Its value is about 4.0. The lowest value, something like cesium or francium, that's about 0.7. So that's about the range. I'm just throwing out the range of numbers we're going to be talking about. A little bit less than 1 is the lowest number for metals way down in the lower left. Fluorine's the highest at 4.0. Carbon, nitrogen, oxygen, are those elements of any importance to people? Those three elements, is that those three plus hydrogen, is that pretty much what life is based on? Organic chemistry, biology, all of that. Carbon, 2.5. 2.5, isn't that almost exactly halfway between the highest number 4 and the lowest number 0.7? So carbon has electronegativity pretty much right in the middle. Nitrogen, 3.0. Oxygen, 3.5. Different tables sometimes give slightly different values, not massively different, but different people have set up different tables, so you might occasionally come across a table of electronegativity that might be slightly different than these numbers. Don't let it bother you too much. These are probably the more common set of values. I went down to chlorine, 3.0. Hydrogen, 2.1. I bet you were hoping to have some numbers you needed to memorize.
Oh.
Those are pretty much the numbers you need to memorize. We've already talked about the trend, particularly if I look at carbon through fluorine. Does that follow the trend? It's getting bigger as I go from carbon towards fluorine. And if I look at chlorine and fluorine, it's getting bigger as I go up. Let's see, don't I have, isn't that a lovely metalloid step? What do you think the value is for metalloids? Would it be bigger or lower than 2.5? Lower, because the metalloids are down or to the left of carbon, so they should be smaller than carbon. In general, we're going to say that nonmetals are greater than 2.0. What do you think metals are going to be in general? Less than 2.0? There are a few weird exceptions. Things like gold and a few of the other coinage metals go slightly over 2, but that's usually a pretty good number, than less than 2.0. Metals are less than 2.0, non-metals are greater than 2.0. What do you think metalloids are? 2.0. Is that an easy way to keep track of the three main groups of the periodic table? Metalloids, metals, non-metals. So cutoff, pretty much metalloids. And we've got these 6 numbers that I want you to memorize. We've got the trend that we could work with. And the sort of way that this information might show up on a test question would be, here's a bond, label 1 atom partial positive, 1 atom partial negative. The more electronegative of the two is the one that's partial negative. The larger the number, the more it pulls electrons towards itself. The less electronegative, the smaller the number, the less it pulls electrons. So in other words, it would lose electrons. we've already done something like this, the HCl, and we'll use that arrow I'm erasing occasionally, but we'll more normally write it something like this. We might do something like throw out carbon to chlorine. When I write out a bond like this, the rest of the molecule is still there, but I'm only looking at a part of the molecule. So don't look at it and get all confused about what happened to the rest of the molecule. The rest of the molecule's there. We're just concentrating on a part of the molecule. So you don't need to try and turn that into a Lewis dot structure or any structure when I write out carbon, line, chlorine. You just need to figure out which side is more electronegative, which has a greater electronegativity value, chlorine or carbon. Well, those are both numbers you're hopefully going to have memorized by the time we get to test 4. Chlorine 3.0, that's larger than carbon's 2.5. So I put a partial negative here, partial positive here. And again, we always put one of each down for each polar bond. Hydrogen, carbon. Again, that's just a part of a molecule. The rest of the molecule's there. We're just looking at a part of the molecule, though. Oxygen to hydrogen. I've got a few example bonds here, hydrogen to carbon, oxygen to hydrogen, silicon to bromine. How about if I let you go ahead and label one atom's going to be partial positive, the other atom's going to be partial negative.